This is the fourth and final lesson of theory of flight. Plate 1 shows an airplane in a very shallow bank and one in a very steep bank. Notice that airplane A has lost very little lift in making its shallow turn. Very little increase in its angle of attack is necessary to increase its lift to the point where it will maintain its altitude. However, in the case of airplane B, there is another story to be told. Since it is such a steep bank and is using so much of its lift to turn the airplane, the total lift of the wing must be more than doubled in order for it to maintain altitude. Now, as you may have guessed, it will require quite an increase in the angle of attack to achieve that much additional lift. You will find that as you approach a 70-degree angle of bank in most airplanes, it is virtually impossible to gain the additional lift necessary to maintain altitude. If you try to pull that far back on your elevator control, you will reach the angle of attack that will stall the airplane. Remember, the steeper the angle of bank, the greater the angle of attack has to be to prevent you from losing altitude. Therefore, as you steadily roll into steeper and steeper turns and increase your angle of attack more and more, you are getting closer and closer to a stall, until finally, when a steep enough turn is achieved, you will stall. Recovering from this type of stall is the same as recovering from a normal stall. Release the back pressure on your stick and reduce that angle of attack. You should be able to see by now that it is impossible to make a 90-degree banked turn and still maintain your altitude. Plate 2 illustrates this point very well. You'll notice here that no matter how much additional lift is available, none of it acts vertically. Gravity is unresisted, and the aircraft will descend. A 90-degree banked turn is perfectly safe, however, as long as you expect to lose altitude. Any attempt to maintain altitude by pulling back on the stick will result in a stall. Stalls that occur while turning are called turning stalls. It is possible to enter a turning stall while in medium banks or even shallow banks. Imagine that you are in a turn as on plate 3. Naturally, you are not stalling. But suppose that while in this turn, you wanted to climb and gain altitude. Due to the fact that you're in a turn, your angle of attack has already been increased somewhat. You are nowhere near a stall. However, your angle of attack is greater than it would be if you were in straight and level flight. This increase in angle of attack is necessary just to maintain your altitude in the turn. Now you want to climb, so you add power, and you pull back even more on the control stick in an attempt to gain altitude. These steps are shown on plate 3. The white arrow represents the normal lift of the airplane in straight and level flight. The gray extension represents the additional lift necessary to maintain altitude while turning. The black extension represents even more additional lift that is necessary if you wish to climb. Remember, the steeper your turn, the closer you are to a stall. An attempt to gain the additional lift necessary to climb steeply will result in an excessive angle of attack, hence a stall. A wing is capable of producing only so much lift. Turning an airplane requires additional lift, and climbing requires additional lift. Attempting to climb rapidly and turn steeply demands more lift than your wing is capable of delivering. Plate 4 shows an airplane in a steep turn. Most airplanes will do this. Plate 5 shows an airplane in a fairly steep climb. Most airplanes will do this also. An airplane will not, however, climb rapidly and turn steeply at the same time. This can best be shown by plate 6. The shaded portion of the bar represents the amount of lift used in straight and level flight. You'll notice the angle of attack is about 0 degrees. Above the normal lift is a large amount of reserve lift to be used when needed. Now assume that we enter into a 45-degree bank. To maintain our altitude, we increase our angle of attack to about 10 degrees. Look at plate 7. By doing this, we have used up approximately half of our reserve lift. We have very little left over. Now, while turning, Let's enter into a shallow climb. Plate 8 shows that we have used all the surplus lift available. We are almost to the stalling point. Any attempt, either to turn more rapidly or to climb any faster, will result in an excessive angle of attack, and consequently, a stall. It is always a good, safe practice to make climbing turns at a very shallow angle of bank. The wings of an airplane can only produce so much lift. Do not attempt to demand more lift than they are capable of delivering. Many pilots are under the misapprehension that an airplane stalls at a particular speed, which simply is not so. Here is a very dramatic way of proving our point. Plate 9 shows an airplane in a near-vertical power-on dive. Our ill-fated pilot is indicating far more airspeed than he would if he were cruising in straight and level flight. As our pilot loses more and more altitude, he decides to rapidly pull back on the stick and commence climbing back to his original altitude. Plate 10 demonstrates very efficiently what happens. Even though our pilot pulls the stick back in a rapid attempt to raise the nose, the airplane has built up so much speed and so much momentum that it temporarily continues downward. Notice that even though the attitude of the airplane has changed from straight down to almost horizontal, the airplane is still going down. The airplane had built up so much momentum during its dive that even though the nose of the airplane was raised, the ship temporarily continued downward. You'll notice that when the airplane is in attitude number 4, it is still going down. Well, if the ship is going down, then the relative wind is coming up, as shown by the arrow. Obviously, the angle of attack is so great that a stall is inevitable. So here is a particular case where an airplane stalled at a very high airspeed. As a matter of fact, an airplane can stall at any airspeed as long as one condition exists. The control stick must be pulled back far enough to obtain an excessive angle of attack. Again, stall recovery is simple. Release the back pressure on the stick and reduce that angle of attack. Well, we've talked about the 3 different types of stalls. The first type, plate 11, occurs with your wings level. The angle of attack is slowly increased to the stalling point. This is called a normal stall. A normal stall can be accomplished with power on or power off. An airplane entering into a normal stall will stall at a slightly lower speed with power applied than when the engine is idling. The second type of stall is the turning stall, shown on plate 12. It is important to learn one thing further about this particular stall. As a turn becomes steeper and steeper, the airspeed at which it will stall becomes greater and greater. For example, a particular airplane may stall at 60 miles per hour in a 20-degree bank. If the angle of bank is increased to 65 degrees, the airplane will stall at 120 miles per hour. The third type of stall occurs whenever an attempt is made to raise the nose abruptly. This is called a high-speed stall or an accelerated stall, and can occur whenever the nose is raised sharply. It can occur at any speed. Just be careful never to yank back on the control stick to raise the nose rapidly. Take your time and always ease the stick back slowly. Never be abrupt. This should take care of the question, at what speed does this airplane stall? An airplane will stall at any speed, providing the proper conditions exist. Now we've talked about turns and stalls. Perhaps the cart has been put before the horse. It has been assumed that we know how to bank an airplane. Plate 13 shows a top view of an airplane. Both wings have a control surface located on the rear end of each wing. Now, these control surfaces are called ailerons, and when moved, cause the airplane to bank. Plate 14 shows what happens when the control stick is moved toward one side. One aileron goes up, and the other goes down. You'll recall that when the elevators go down, the tail is forced up. The same thing is true of an aileron, and for the same reasons. When the aileron goes down, the wing goes up. So in the case of plate 14, the left wing will rise. By the same token, when an aileron moves up, it forces the wing down. If the control stick were moved to the left, as on plate 15, the airplane would bank and turn to the left. The raised aileron will force the left wing down, and the lowered aileron will force the right wing up. All this may seem a little basic, but be patient, we're leading up to something. There are 3 primary controls on an airplane. We've discussed 2 of them, the elevators and the ailerons. The third control is probably the most frequently misused control on an airplane, the rudder. Plate 16 shows how a rudder turns a boat. Many students unknowingly try to turn an airplane in the same manner. They don't realize that a turn is affected by banking. Plate 17 shows the rudder on an airplane. It is very simple in appearance and even looks like the rudder on a boat. Well, if a rudder doesn't turn an airplane, what does it do? It is essentially a corrective device. Let's see how it is used. Imagine that we want to execute a turn to the right. The stick is pushed to the right, and the ailerons are deflected as shown on plate 18. The left wing rises, and the right wing goes down. We are now banking to the right. Plate 19 reveals an unusual situation. The left wing is creating much more drag than the right wing because it offers a greater surface for the air to hit. Now we're in a right bank, but the left wing has more drag than the right wing. Plate 20 shows the results of this adverse effect. Since there is so much more drag on the left wing than on the right wing, the airplane will veer to the left, even though the airplane is banked to the right. The rudder, as shown in Figure 21, is used to counteract this effect and allows the lift of the wings to turn the airplane. Once the desired angle of bank is obtained, the ailerons are neutralized. Both wings then have an equal amount of drag, and the rudder is no longer needed. The airplane will continue turning on its own. When it comes time to roll out of the turn, opposite control of the ailerons are applied. As soon as the ailerons are deflected, an equal amount of rudder pressure must be applied. Remember, the main purpose of a rudder is not to turn the airplane, but to counteract the excess drag effect on the wing exerted by the down aileron. The rudder is used when the ailerons are used, at the same time with equal control pressures applied. Always coordinate the ailerons and the rudder. Plate 22 shows a pair of flaps located on the trailing edge of the wing between the ailerons and the fuselage. All but the smallest airplanes are equipped with flaps. They are similar to ailerons, except that one flap will move downward at the same time and angle as its companion flap on the other wing. This is shown on plate 23. Flaps serve to change the lifting capacity of the wing by changing the camber of the wing. When lowered, flaps will increase the lift of a wing for any given angle of attack. But along with producing additional lift, additional drag is also created. Flaps are designed for use at low speeds and have no purpose whatever at normal cruising speeds. In fact, most aircraft manufacturers prohibit the use of flaps at high speed. Not being intended for anything other than low air speeds, flaps are not stressed or beefed up enough to safely undergo the forces encountered in normal flight. Airplanes with flaps will have a maximum speed at which their use is allowed. Plate 24 is an excellent illustration of how flaps are used. You are approaching an airport for a landing in a normal glide with the engine idling. You notice that you are too high and are overshooting the airport. Normally, when one wants to lose altitude, all he would have to do is reduce his engine power. However, in our case, the power is already reduced as much as possible. Diving wouldn't solve our problem because too much airspeed would be built up, and by the time we do reach the runway, we'll be going so fast we'll be unable to land. With flaps, however, we could lower our nose and lose altitude without fear of excessive airspeeds. The large flaps have so much drag that a rapid descent can be made at a reasonable approach speed. Along with this advantage, flaps also, by changing the lifting capacity of the wing, reduce the speed at which an airplane might stall, and hence provide for lower landing and takeoff speeds. This is the end of Lesson 4, and consequently the end of theory of flight. No attempt has been made here to teach you how to fly an airplane. Rather, the purpose of this record is to increase your pleasure and safety in flying by explaining briefly and simply some important facts that have been learned through pilot experience, engineering research, and accident analysis. This record cannot be considered a substitute for a flight instructor. It does, however, explain some of the reasons for your instructor's emphasis upon certain procedures and techniques in flight. Oh, by the way, the examination for Lesson 4 is in the back of your manual. Good luck.